We've now investigated Euler's method and we know how to do a lot of things with it, but is there a better way? And it turns out that there are two better ways, and one of those is called improved Euler's method and the other one is called RK4, named after those credited with it. So one of the things we know about Euler's method, its disadvantage is in approximating the values of y is that error compounds quickly even as we decrease step size. Ultimately, error will just continue to snowball no matter how small of a snowball you start with. Now, one improvement that we could potentially do is it turns out that we could actually take the average of two slopes, right? So it's kind of like Goldilocks and the Three Bears. If you ever heard that story before, it's like, well, this soup is too hot, this soup is too cold, this one is just right. So what we can kind of envision is if we come up with a slope and we find out that, that's really overestimating the true slope, and then we take a slope at another point, we find that that one's kind of too small. Well, if we take these, and I'm just going to write it like this, if we add those two slopes and divide by 2, then we'll get something that's just a little more reasonable, and that ends up producing a better slope. And that's exactly what we're going to do. Now, notice that the computation is exactly identical. To get the new value of y, you're going to take the current value of y and add an average of two slopes to it, multiplied by your step size, right? So this could have units of, say, elk per year when you average together two slopes. And you have to multiply that by the number of years so that you would determine how many more elk you would have at that time. So we typically call K1, we use that to indicate slope 1, and K2 to indicate slope 2. Now we're not going to get into the computation of this because it does get more tedious to get those two slopes because the slope K2 actually depends upon the slope K1. So this is just an alternative way to write it. Instead of having written slope 1 and slope 2, we'll use K1 and K2. So what should K1 and K2 be? Well, because we understand Euler's method, K1 is exactly the slope that we came up with in Euler's method, and that is at our current point. Let's just t0. This doesn't have to mean time 0. This is just our current value of time from which we're iterating. So here, remember what we did is we took that ordered pair, whatever that y was right there, y0, and that's the ordered pair t0, y0. And then what do we do with that? Well, we got a slope, right? We took that and plugged it into dy dt, which notationally we like to write it this way because of the fact that this allows us to see what input value of y we're plugging in. And so what we would do is we get the slope of this red line, which would be called K1. And then that's exactly the same thing as in Euler's method. So this is same as the standard Euler's method. And then what do we do to get K2? Well, we did before. We took that slope that we got right there, and then we used that, multiplied our rate by delta t, and added it to our current value of y. And then we came up with this new point right here, which in this case, notice that this is the real solution curve. In this situation, we're kind of under, right? So this is our next point right here. And that's exactly the same thing that we did in Euler's method. Except now, what we're going to do is we're going to take this point that we got, and we are going to compute the slope based on that ordered pair right there. So next, get the slope f of t1, y1. Okay, so now you take that point, and this seems just exactly like Euler's method, right? That's exactly what we do in Euler's method. We plug that point into our ODE, our ordinary differential equation. That would give us a slope. And then what would we do with that slope? Well, then we would move on from there, right? We would use that slope. Let's say at that point, you get a slope that looks like that, and you'd use that to project out to time t2, and you'd get a point there. But we're not going to do that. What we're going to do instead is we are going to grab that slope right there, okay, whatever slope we get right here, we're going to record that as f of t1, y1. And guess what? We are going to call this slope right here, we're going to call that slope 2. That's going to be our K2. So one slope we get right here, and then by using Euler's method, we get a new point which gives us a new slope. And then we're going to take right here plus this slope right here and average them together. Okay, so now we would take k1 plus k2 over 2. This is going to be our actual slope. And then we're actually going to kind of rewind. We're going to come back to t0 and we're going to use that slope instead. So take this slope, right? I'm going to draw them over here like this and like this. We take those, we average them together, we get something that's slightly less steep. There it is. And then we come back and then use that slope that, I guess it should be in this case a little more steep, right? Because we're averaging, yeah, this guy should be a little more steep than I've implied, just based on our picture alone. This is less steep, more steep, so the average of those will give us kind of something in between, right? So then we take that slope, and that's what we actually use to project to get us to our actual T1, Y1. Okay, so it's kind of weird, right? It's like kind of you're using Euler's method to go forward, but you don't actually go forward. You just go forward for a moment so that you can gather the slope at that new point. And now you have a second slope. So the actual slope that we'll use will be the sum of those two slopes divided by 2. And that's the actual slope that we'll use at T0. Now at T1, we'll do the same thing. Right, we'll get the slope there. We'll move to T2. We'll calculate the slope there. Call that K2. Take K1 plus K2 divided by 2, and we'll move forward progressively. Now, we won't go through the computation of this because it does get a little tedious, right? You have to compute two slopes, then you have to average them, and then you actually have to start back at your starting point and use that as your actual slope to get you to T1. A lot of times you'll see H used instead of delta T. That just makes it a little bit easier. And in that case, this is what it would look like. You'll often see it written like this, which looks just like Euler's method. This divide by 2, you could write it as H over 2, or you could write it as H times K1 plus K2 over 2. And to get K2 here, remember, here this is our slope at our current point. And then here we're computing the next point, right? This is the next point. This is actually what we would call the next value of t, and this is what we would call the next value of y. And that's exactly what we were computing over here when we had t1, y1. All right, enough of that. Turns out we don't really even use improved Euler's method, right? Because even then, the slopes are approximate, they have error in them, and then, well, we start to compound error more and more quickly. So if we can find out, and we'll do this in a moment, in another video, we'll show how improved Euler's method is actually better than Euler's method. And so that might bring us to think, well, should we use two slopes or should we use more? Is it the case that more is better? Well, yes and no. As it turns out that if you go beyond 4 slopes, and by the way, we would say that this is fourth order. It's a fourth order method if you're using 4 slopes. Improved Euler's would be second order, and then Euler's method would just be a first order technique. The amount of precision gained is negligible beyond using 4 slopes in comparison to the workload, right? Even using computers will get bogged down if you give them too much work. And you give them more work, they get more bogged down, but the trade-off is not beneficial. It turns out beyond 4 slopes, you don't gain an incredible amount of accuracy. So I just want you to think, when you look at this, okay, wow, this looks complicated. But here's what's going on. K1 is always basically just your Euler's method slope. Even in this method, RK4, which is often just spoken as RK4, we still get K2 in the same way that we got K2 in improved Euler's method, right? So we use the K1 to get us to the next point, the next value of time. Okay, that's just written as, in RK4, though, we actually only go half of the distance between our points, which we could think of as h over 2. Then we get a slope called K2. Now notice that this slope, what we do next is we back up to our starting point, and then we use K2 to get us to this new point over here, which at that point we compute this slope called K3. Then we take K3 back to the original, so this is just like a bunch of iterations of improved Eulers, and then we use that slope to get us to the end of that interval, oddly enough, instead of the midpoint of that interval. We get a slope called K4, and then once again we step back. Now what do? Well, we take K1 plus K2 plus K3 plus K4, and we divide by 6. What? Why 6? Well, hold on. It's actually 2K2 plus 2K3. And this all boils down to a bunch of calculus and what we call the Taylor series approximation, which kind of gets a little complex as far as this derivation is concerned. But what we should take away here is that K2 and K3 are doubly weighted. They get twice as much weight as K1 and K4. It's basically as if we've taken 1 plus K2 plus K2 plus K3 plus K3 plus K4. So we have 6 slopes, but it's just 4 of those slopes are, 2 slopes are copies, and as well as the other 2 slopes. Okay, obviously we're not going to do this by hand because getting these slopes is incredibly tedious. And, you might see something written like this. I just want you to notice that it's exactly the same kind of logic as Euler's method. But in this case, you're computing 4 slopes. 2 of them get doubly weighted. And then, to get the next value of y, you take your current y plus step size times the average of these slopes. So it's still called fourth order, even though it utilizes, technically 6 slopes. Just keep in mind that there's only 4 distinct slopes, K1, K2, K3, and K4. This is what you might see in a textbook. Kind of looks ugly, not super fun to calculate by hand. Then, question we might ask is, well, what kind of step size do we need for RK4? For us, usually 0.1 will be pretty good. Depending on the technology, 0.01 could work better, but 0.1 is typically pretty reasonable. And as a result of RK4 being the best, that's going to be our go-to tool. We're going to spend very little time doing anything with Euler's method and improved Euler's method, because as you see, they're not as good. And why would we waste time? The only thing is, to use this, we're going to need some technology, which we will investigate.